Okay. Okay, so hi everyone. It's a pleasure to have today Amos Yarom from the Technion, who will tell us about holographic turbulence. Please, Amos.
Okay, thanks. So yes, today I'm going to talk about holographic turbulence. I've targeted this talk towards an audience who has a good knowledge of gravity. And what I want to do is relate certain aspects of certain black hole physics to turbulent flow. So the word holographic means is sort of a placeholder for a certain set of relations between field theories and gravity. It goes under the name of ADS-CFT or gauge gravity duality. I'm not going to assume you know anything about this, and I'm really going to use only a sort of a very particular way of looking at it. So let me start by reminding you a little bit about the Navier-Stokes equation. So this is the Navier-Stokes equation for incompressible flow. V is the velocity field. Here we have a time derivative, spatial derivative. E is the pressure field, and nu is a viscosity, and F is an external force. So I don't know, a motor, gravity, anything you want. There's one kinematic equation, a time-dependent one, and one constraint equation. And the variables we're solving for are the velocity field and the pressure. Everything else is given. Now, this simple-looking set of equations describes many phenomena on very different scales. And a lot can be said about this set of equations, but what I want to talk about today is turbulence, and by that I just mean macroscopic turbulence that I think you're familiar with. One characteristic of turbulence is the Kolmogorov scaling of the kinetic energy. So what does that mean? If we define the kinetic energy for the fluid per unit mass between some momentum k and k plus delta k, then what Kolmogorov says is that this quantity should scale like the momentum to the minus 5/3. This is called the 5/3 law. And this is a prediction, and it's realized in many experiments and simulations. So here, what you see on the horizontal axis is the momentum. What you see on the vertical axis is the kinetic energy density, and there's a range of momenta where this 5/3 scaling is observed.
Is this Kolmogorov?
What do you mean by it?
Kolmogorov law?
Yes.
Okay, good.
Yes. The numbers change if you go from real space to momentum space, and you can also do some other things, but it's all Kolmogorov's law.
Okay.
I'll talk about the derivation in a bit.
Okay.
Okay. Now, to obtain this result, something's not working properly. So to obtain this result, one needs this driving force. The circle should have been on the driving force. I don't know why it's shifted. Anyway, this driving force is needed so that the energy, the kinetic energy, is density will be time independent. So you can imagine that if you inject if you start from some initial state and you let the system evolve in time, if there's nothing that supplies energy to the system and it's infinite in extent, it'll just relax to some state where there's no velocity. So all the kinetic energy is going to be clumped at zero velocity. In order to get a configuration like this, which is time independent, we need to supply power to the system, and that power is supplied by this driving force. So some force, we act on the system with some force, and that supplies energy to the system. This parameter is called the viscosity, and what happens is that that generates heat, and then there's a balance between the energy or the power that's supplied by the driving force and the friction that goes to heat, and we reach a steady state, which is time independent. And once we reach this time independent steady state, then this prediction should work, and that's what we're seeing in this plot. So if there's no time axis here, this is a snapshot in time, but it doesn't change in time. You can actually average over time, and it'll be like spatial averaging, as you'd expect from a steady state.
Amos, can I ask a question?
Now,
so what sets the range in which you have this k to the this behavior, like where this behavior ends and starts?
Yes, this is a good question. I'm going to answer it now.
Okay.
So yeah. So this particular simulation, and most of the simulations of turbulence, rely on having an external force. And what one usually uses is a random force. So it's a force that can, whose average is 0, but its correlation functions are non-zero. And of course, the power that's applied, which is the velocity times the force, average of that is also going to be non-zero. So one usually uses a driving force which comes from some ensemble, and when we plot the energy density, it's actually the energy density that's averaged. So this bar just means that we're averaging over an ensemble, and the ensemble in this case is an ensemble of driving forces. And in order to generate this particular steady state, what one usually does is supplies the driving force at a particular momentum. So in this case, the momentum is of order 1 inverse centimeter. So the driving force is at a scale which I denoted kf. F is for forcing. So that's the scale where we put the energy in. And then there's a scale where dissipation occurs. So that's usually denoted by kd, d for dissipation. And the range where we see this power law is between the range where the force is injected and dissipation occurs. This is called the inertial range, and that's where we expect to see this power law. So this predicted power law it's really, there's a lot in here. We're assuming that there's a force at a particular scale, and that scale should be, well, if we're looking in momentum space, it should be smaller than where the dissipation occurs. And if everything works properly, then the prediction is that we'll get this minus 5/3. Okay, so how does the argument go? And I'm really just going to sketch it. You might have heard that this is just dimensional analysis, but it's not quite just dimensional analysis. You need to invoke some physics before just saying dimensional analysis. You need to really say, what are the quantities that physics in the inertial range is going to depend on? And once you know those quantities, then it's just dimensional analysis. So the argument is roughly as follows. The first thing that we say is that there exists a range of scales, which is the inertial range, where the limit when the viscosity goes to 0 of this quantity is non-zero. This isn't the way Kolmogorov originally stated his argument, but this is the modern way of presenting it. So this expression here is the symmetric derivative of the velocity field. This is sometimes called the shear tensor. And by squaring it, I just mean, contracting, writing it twice and contracting the indices with themselves. And the viscosity that appears here is important because this expression altogether really tells us the amount of energy that's being dissipated eventually in the system. And the claim is that when we take the viscosity to zero, this quantity is not zero, but it takes on some finite value, which means that the shear tensor should diverge. This is a conjecture, but I think the community now agrees that this is correct. Obviously, you can't really take the limit where the viscosity goes to zero, but in all the simulations that one does, it seems to converge to a value which is non-zero.
Amos?
Yes.
In order to take the limit n goes to zero, you need to specify not only what happens to n in this limit, but also what happens to the other parameters, specifically the force and the initial conditions.
No. So yes. So yes, you're right. I mean, everything is going to depend on the force and the initial conditions. So the forcing is kept the same. You want the driving external momentum at which you drive your system to be the same relative to the dissipation scale. And the initial conditions don't really matter much because once you're in a turbulent regime, the initial conditions, it's a chaotic system. So the initial conditions aren't going to do anything for you. But you do want the force to be taken from the same type of ensemble. So you don't want to change the ensemble of the driving force, even though that also doesn't change much. So you want to keep everything fixed if you take n to zero.
Okay, thanks. So the shearing will diverge. What about the velocity itself? You're not saying anything necessarily about that. The velocity field,
No.
the shear of the velocity field will diverge.
Shear squared, yes.
And what is the physical meaning of this equation?
So again, this quantity, viscosity times shear squared, if you integrate that quantity, that's the energy loss. So what this means is that if you let me write an equation. So if you look at the total energy, you look at the total energy per unit mass, right? So this is just the total kinetic energy. If you don't have the driving force, then what you'll find is that the time derivative of the total energy is equal to minus nu integral di Vj plus dj Vi squared d3x. Okay, so this quantity here is sort of the amount of energy that's being dissipated into the system.
Okay,
and so what this is telling you is that in the inertial range, this quantity is constant even at very, very small viscosities.
So it's surprising, no? Because you'd think that as you take n to zero, the dissipation would go away, but instead you say it remains fixed in the limit.
It's very surprising. It means that if you set this term to zero and solve the equations, you're never going to be able to reproduce this. So the limit as the viscosity goes to zero doesn't coincide with the zero viscosity solution. This is called a dissipative anomaly, and it's surprising. Yes, it is.
Okay, thanks.
This is not a trivial statement.
Yeah, so it's not an argument, but it's a step. Okay, it's something that needs to be demonstrated, and then you can go to the next step.
Yes.
Okay.
Yes.
It's not something that was obvious to us.
It's not obvious. No, it's not obvious. Okay. Good. And so, so this is one statement we're making, and the second statement that's made is that in this inertial range, all the physical quantities are just going to depend on this dissipation rate E0 and on R, the scale at which we're probing the inertial range. And once you say this, then it's just dimensional analysis. Now, any quantity that we look at we should be able, by dimensional analysis, to say how it depends on these two parameters. So, for example, if we look at some nth power of the velocity difference and we average it, ensemble average it, then we're going to get this behavior here. Okay, and if we go back to, pardon?
What is n?
N is, yeah, whatever power you take of the velocity difference.
Oh, okay. Okay. Yeah, thanks.
So this n here is the same as this n here.
Okay, okay.
Amos, one thing is still unclear to me regarding the first assumption that we don't see it now about the limit.
Yes, one second, I'll bring it back. Yes.
The quantity at the left-hand side, is it a function of R or you kind of integrate over R in that range?
Well, yeah, so yeah, I'll make this more precise in a bit. But the statement, yeah, so you have to say what you mean by what exactly depends on R here. So yes, you need to do some integration to really make this definition precise. And I'll do that in a bit. This is a good point.
Well, I suppose you have 2 points separated by distance r, and by homogeneity, it doesn't matter which points.
That's right. But at this point, it looks like a 1-point function, not a 2-point function. So you need to be more, yeah.
Okay.
But yeah, so you need to do something. Either think of it as a 2-point function, or integrate, or something like that. It doesn't really matter what you do. You still get the same type of behavior. The value of E0 might be slightly different, but that's not going to change the dependence. The dependence on R, power law behavior.
R stands for a typical scale.
Yes.
Okay. Because I would imagine that if I look at a given R, well, at the center of that range of R, then when I take n to 0, then these quantity, the shear, will go to a constant at that R scale. And then, of course,
I agree that this is what you'd expect, but it doesn't.
even if I specify my R.
Yes. So what you have to do is really sort of average this over some spheres of size R. And if you do that, then it's going to diverge.
Okay, I average over a sphere. Okay. But then,
yeah, because R is meaningless. I mean, like Barak said, this is homogeneous. So the value of a particular point relative to a coordinate system is that's not what R means here.
Okay.
It means a typical patch that you're looking at.
Yeah. Okay, I can ask you more questions later on.
Okay. Okay, so the energy power spectrum is what I call the kinetic energy per unit mass. The power law behavior k to the minus 5/3 is, you can really get it from the n equal 2, setting n equal 2 in this expression here, and then Fourier transforming the velocity squared will give you eventually this minus 5/3 law. So I won't go through this exercise, it's straightforward. All I'm saying is that this is a special case of this. Okay. And again, this also has been studied. Here's this is a rather old example of what happens for n equals 3. You get a result that looks like this. Now, I think not very recently, but not too long ago, it was understood that there are some deviations from this power law behavior. So this is the theoretical prediction for the power law behavior here. This axis really tells us, gives us this power, and this axis is n. Okay, so we compute this thing and divide it by log, take the log, divide it by log r, and then it should depend on n linearly. It should go like n over 3. So this line here is just n over 3. So this is what one expects in theory, and this is what one finds in experiment. So yeah, for small values of n, the experiment gives something higher than theory. This is a numerical experiments most of the time. And for higher values of n, it's lower. And exactly at n equals 3, it coincides with theory, but n equals 3 is the only case where you can actually prove this. So for n equals 3, you can actually prove this relation precisely. When I say this relation, what I mean is that you get this behavior. So exactly when n equals 3, there's a proof, and then it obviously coincides with the experiment. But in other cases, this just doesn't quite work. Okay, so the challenge here is to try and figure out how to predict this.
An experiment is numerics.
There are some non-numerical experiments, but I don't think they go to very high values of n. So to high values of n, you need numerics, and you need very good numerics, because when you take larger and larger powers, you lose your precision.
Yeah, what I asked is, numerics is what's called here experimental or theory? Or
Experimental. I mean, numerics, but I mean, when I say experiment, I mean theory. When I say theory, what I mean is there's some theoretical prediction. The theoretical prediction is based on these two assumptions and some hidden assumptions, which I didn't talk about, like homogeneity and things like that.
okay.
So that's what I call theory. And when I say this, I mean, it's not that you take the Navier-Stokes equation and you don't make any extra assumptions, just that these equations are satisfied, and that's what you get. So that's not what I call theory. What I call theory is what's written now on the slide. It's these two assumptions. Experiment means that I actually just use the equation itself, and I just solve it. I solve the equation and I see what I get.
Amos, I think you could avoid this confusion if you replace in the figure experiment by simulation. And then really, because it's not really the same thing.
Yeah, I have no.
Okay.
There we go. Okay. So now, of course, the question is what goes wrong, and we don't really know what goes wrong. We'll know it once we can fix well, either sort of actually have a proof like we have in the n equals 3 case, or we fix our assumptions and use that to make a prediction which would agree with simulations. But I think what's currently agreed on by the community is that maybe the problem is that when we take the average of the sort of energy flux in the inertial range to the power of n, it's not like averaging and then taking the nth power. If this is the case, then yeah, the slides aren't working for me now. So if I average, you should ignore this thing. If I average the quantity on the right, then this is not the same as first averaging and then taking the n to the third power. And if that's the case, then this averaging, essentially the averaging of this quantity and then taking its nth power might have some R dependence, and that's going to affect the overall dependence here. So what one can do is to define this quantity, which is an integral over the shear squared. So this quantity, the circled quantity, is the shear squared, and it's being integrated over a region of size big R. Okay, and V of R is just the volume of that region. So we're sort of looking at the average shear in a region of size big R. And like Barak said, we don't expect this to depend on X. We don't, if it's homogeneous, we don't expect to care whether we evaluated this around X equals 5 or 0 or 117. It should take the same value, but it might depend on R. And so if it depends on R like R to some psi, then this psi is going to modify the power law behavior that we have here, because we're going to have an extra factor of psi coming from this average. And so this psi that appears here will affect the psi that appears in the plot.
What
So
is the
psi.
What is the relation between capital R and small r? Or there
Well, maybe I should have used small r. I didn't know what would be more confusing. So capital, one second. Capital R is the R that appears here. So what you're doing is you have some fluid, and then you're choosing some X, and then you're looking at a sphere of radius R around that X, and you're averaging this quantity in that sphere. So this is going to depend on X and on the radius that you averaged. So that's this X dependence and this R dependence. So this big R which is the radius or the volume radius of the sphere, that's going to really tell us where we're sitting in the inertial range. So this is the average that you talked about a few minutes ago.
Yes, okay.
So this would be a more precise statement of saying that this quantity is a constant. It would mean that it's independent of this. Oh, this is too messy now. It means that little e of R would be independent of R.
Yes. Okay. Good.
Is that, yeah. Okay, so this is an open problem. Nobody knows the answer. It's one of the biggest, I think, problems in classical physics, understanding turbulence, and that means, I think, if one can make a prediction for this blue curve, that would be significant progress. So now let me go to something that looks completely different, and that's black holes in anti-de Sitter space. Unless there are questions. Okay, so I want to look at anti-de Sitter black holes in anti-de Sitter space, and before talking about black holes in anti-de Sitter space, let me just talk about anti-de Sitter space. So I think the majority of you know anti-de Sitter space in this type of coordinate system. So this is a solution to the Einstein equations in the presence of a negative cosmological constant. The Penrose diagram is going to be sort of a rectangle that's infinitely extended in one direction, which is the time direction. And then the other direction in this diagram is the radial direction. So rho equals infinity is the boundary, and rho equals 0 is the center of EDS space. Now, often it's useful to consider a two-dimensional Penrose diagram where the angular coordinate is also represented. So the two-dimensional Penrose diagram would look like this, and the extra circular direction represents a two-sphere. So this is ADS space. And And there's another coordinate system for ADS space, which is called the Poincare patch. So what you see on the right is the Poincare patch of ADS space. It still describes anti-de Sitter space, but it doesn't cover all of the space-time. So in this cylinder diagram of space of ADS space as a cylinder, the Poincare patch covers only a patch. So it's sort of it's whatever is inside this diamond region that's covering the cylinder. So I could use infinitely many of these patches to cover the entire ADS space. So in the coordinate system here, you can see that something funny is going to happen at r equals 0. Of course, ADS space is not singular, so this is going to be a coordinate singularity. It's called the Poincare horizon, and it's where we exit or enter the patch if we look at it from a global perspective. Okay, so these two coordinate systems describe the same space-time. One of them covers only part of it, and the other everything. Now, if I talk about a black hole, there are two types. Well, I want to talk about two types of black holes. The first one is a black hole in the coordinates that originally covered the entire ADS space. So like in the Schwarzschild case, you have some function h, which encodes a mass term. And whenever this function h vanishes in this coordinate system, we have an event horizon. So in the picture before, what we have is that we have an event horizon at some radius r equals r, rho equals rho h, inside far from the boundary. Now, this is no longer a Penrose diagram, in the same sense that the Schwarzschild coordinates covered only part of the space-time. Here too, this diagram covers only a part of the entire space-time. The Penrose diagram for this black hole is similar to the one that you have for a Schwarzschild black hole. There's a Kruskal extension. So the Penrose diagram takes the form on the right. And the coordinate system that you see, this coordinate system here, it really just covers one wedge of this space-time. So this is very, very similar to Schwarzschild. Okay, now we can...
Question about the Penrose diagram.
Yes.
I remember that the top and bottom lines are not straight except for some specific dimension. Do I remember correctly?
Yes, there is some story there that is not going to be relevant for us, and I'm not going to get into it.
Okay.
Yeah. So yeah, you could say something about the nature of
it's not always straight.
It's not always straight. Yeah, so it has to do with the nature of the singularity, that it's not always space-like. Yes. Okay. So now what we could do is say, what happens if we look at a Poincare patch? So if we look at this from the point of view of an observer who only sees a patch, we're going to see something very funny. We're going to see sort of a black hole emerge out of the Poincare horizon. It'll grow, and then it'll shrink back and exit the Poincare horizon. Of course, there's nothing dynamical going on. This is just a coordinate transformation. We're trying to look at something that's static in a coordinate transformation where it looks like it's being dynamical. But it's just a coordinate transformation. So the space-time is exactly the same. So you can do this. This is a difficult exercise. This isn't what I want to focus on. What I want to do is start from this patch and look at a black hole that's associated with this type of coordinate system. So it turns out that there's a black hole that takes this form on the right. So you see this is, again, it's very, very similar to Schwarzschild. You have this f of r here, which is going to vanish when r equals r naught. And this describes a different type of black hole. So the Penrose diagram for this black hole is going to look the same as before. The Penrose diagram, I remind you, only encodes the time direction and the radial direction. And the coordinate system here is just going to cover one wedge of this black hole. So I hope I didn't confuse you, but the point is that there are two black holes that we can discuss. Right? There's this black hole, which we started off in coordinates that cover the entire space-time, and then we got a black hole in that coordinate system. Or we could start with this coordinate system where we just look at a patch and then consider a black hole there, and we get a different black hole. So the reason they're different has to do with the extra coordinates that we have that are not associated with the time in the radial direction. Here, we have a two-sphere that's associated to each point in the Penrose diagram, whereas here we have an entire plane that's associated with each point in the Penrose diagram. If I freeze time and look only at space, I'm going to get some picture that looks like this. So, you know, there's the event horizon at some value of rho, and there's infinity, which is at rho goes to infinity. And if I take the line element there, it's just gonna look like time times sphere. So this black hole has an inside and an outside and a singularity. On the other hand, here, the extra direction is an entire plane. So at some value r equals RH, I'm going to have an event horizon, which is now planar. And I'm going to have infinity, where the line element is going to take is going to be proportional to this expression here. So these space-times are just different. They're topologically different. Their behavior is different. The event horizon is if I look at a slice of the event horizon, it's compact when it's a black hole, and it's not when it's a black brane. Here too, though, I have an outside. Whatever's between infinity and the event horizon is the outside, and there's an inside, and there's a singularity.
So the metrics are locally, they coincide locally.
Pardon?
The two metrics are locally, they are the same locally, right? Only the global
Yes.
structure.
No, what do you mean? What do you mean? I didn't hear. Are you saying they're the same locally or not the same locally?
The same.
No.
No?
They're not the same locally. No.
Both of them are maximally symmetric, or only one of them?
Well, they're not maximally symmetric because you have a black hole.
Yeah, okay, right. So, yes, okay, I got it, yes.
Okay, but they're different. They're not locally the same. They're really, really different. You have two types of black hole solutions. The difference has to do, if you want, with what sort of symmetry you're trying to keep.
Yes.
Because here you want the spherical symmetry, and here it's planar.
Sure. Okay.
Okay, so even though in astrophysics we're interested in black holes, here I'm going to be interested in the black brane solution. And the reason I'm interested in this black brane solution is because this is what's going to be related to hydrodynamics. Okay, so astrophysically, there's no interest in asymptotically in anti-de Sitter space or in anti-de Sitter black holes, but here, for reasons that I want to explain, they are interesting. Okay, so now let's think of a black hole where I perturbed it somehow. I threw something in, or I have some initial conditions where it's a little bit outside of its equilibrium configuration that it likes. So in this case, the metric is not going to be what I wrote, but it's going to be some corrected metric that'll tell us how the event horizon is jiggling around. And to find out what the metric actually is, we need to go back and solve the Einstein equations. Now, the magic is that if you organize your perturbation theory in the right way, then you can show that this set of Einstein equations is exactly a solution to this set of Einstein equations is exactly equivalent to a set of solutions of relativistic hydrodynamics. So relativistic hydrodynamics, you essentially have, you might be familiar with this expression when you look at some cosmological solutions. U is a pore velocity, P is a pressure term, epsilon is the energy density, and there could be a shear term here, which I didn't write. And conservation, energy momentum conservation, gives us some equation for these quantities. And that's going to be a relativistic version of the Navier-Stokes equation. And the claim is that this set of equations, there's a one-to-one mapping between this set of equations and this set of equations. To see this, you have to organize your perturbative expansion in the right way, and then you can really prove that these two are equivalent. It's not a sophisticated proof. It's really just plugging in the right ansatz into this equation and showing that the resulting Einstein equations are this. So it's something very technical that I think any one of you can just do. Okay, so the statement is that the metric components should be decomposed in the right way in terms of what would be interpreted as the velocity field and energy density. Okay, so there's a mapping between solutions to relativistic hydrodynamics and dynamics of the event horizon. Okay, so this is something that, again, is, it might sound unusual, it might seem weird, but it's something that's, the way I described it, it's just very technical. If you know how to organize your perturbative expansion right, you can just show that there's this relationship. And now, obviously, we can look at a solution which is moving at velocities which are much, much smaller than the speed of light, and we should have something that that looks like the Navier-Stokes equation. Okay, so when I talk about holographic turbulence, what I mean is a relationship of this type.
Amos, so maybe a philosophical question. So I understand that you can derive this relation, but why did it have to be this relation that works? Why did the perturbations of the horizon have to? Is there some way to understand this without doing the
Yes, I mean, it's essentially, well, it's part of a much bigger picture where you can show that there's a certain family of quantum field theories that can be described precisely by dynamics in a certain limit, they can be described precisely by dynamics of anti-de Sitter space. So if you ask, you can describe scattering in these theories, you can describe the spectrum of these theories, and you can also describe thermal states in these theories. And so, when you talk about hydrodynamics, you can think of them as perturbations of a thermal state, and then this is just a very, very particular instance of the ADS-CFT correspondence. Can you see this without resorting to ADS-CFT? Well, people try to do this. I mean, the membrane paradigm is sort of a very early attempt at trying to make this type of relation. So if you want, this is a very fancy membrane paradigm, but here you really get a viscosity that's positive and a fluid that really, this is a real fluid that you're describing. A real, I mean, you can write a microscopic theory that this fluid is describing.
Amos,
Thanks.
one issue confuses me. Here we have the Navier-Stokes equation for an incompressible fluid, which is not a causal theory. How about the gravity side?
No. So yes, so you know the answer to this because we described it and we talked about it. But so you take a limit here. This limit, when you go not only below, you want to go not so. If you take the velocity to be smaller than the speed of light but bigger than the speed of sound, you'll get compressible flow. But here I'm assuming that I'm taking it to be much, much lower than the speed of sound. So what you'll get here is incompressible flow.
Okay, good.
So so this is really an approximation. There are going to be compressible corrections to this. So it's really, we're using incompressible equations to describe something that is compressible, but the amount of compressibility is small. So there are going to be corrections to this equation coming from both compressibility and from having a non-relativistic limit.
Yeah, so the comparison or the mapping between the two theories is at the level after you took the limit in which it becomes incompressible.
The mapping, the precise mapping is this one where this is compressible.
Oh, okay, I get it.
That's the precise limit. Then I'm saying, fine, let's look at velocities which are small, so I can approximate this with this. I actually did a double-edged arrow here and just a single arrow here. You can't go back.
Okay.
This works only one way, right? You can't really go back to here if you have only this solution.
Okay.
So what I'm saying is, yeah, I just say if this is a good enough approximation, I'll be happy.
Yes, but the mapping is already at the level of compressible.
Yes.
Thank you.
Yes. Relativistic flow is compressible.
Yeah.
Okay. Okay. So so now it's a matter of actually checking whether we can reproduce stuff using gravity. So one of the early checks of some relation of this type was done by a group at MIT, and what they did was they solved the Einstein equation, and then they used this mapping to translate it to a fluid. And what you're seeing here is really a fluid behavior that's associated with this type of flow. And this fluid is turbulent. And what these guys did was they computed the energy power spectrum, and this is what they got. So you see here something that you might call minus 5/3, and then say maybe there's an inertial range. You might argue with this, and I don't know if I'll if I can really.
Is this experiment behind gravity or in fluid dynamics?
This is gravity. This is gravity.
And what is the forcing? Did you mention already?
Good. So let me talk about that. That's a good question. This is exactly what I want to talk about now. So remember that we had this picture here. So what we're comparing is something where we don't have any forcing, right? Because we're just reproducing the Navier-Stokes equation, incompressible, versus something where we have some extra driving force. And again, the circle is in the wrong place. Yeah, somehow, sorry. So if we really want to compare things correctly, what we should do is we should compare turbulence without forcing to turbulence without forcing. And when I say what people mean by turbulence which is not forced is something a little different from what I started with. what you do is you excite the system, and then you wait, and then it becomes turbulent, and then you take a snapshot at just the right time of the energy power spectrum, and you might see a minus 5/3 law. This is called decaying turbulence. The problem with decaying turbulence is that it's decaying, it's time dependent. So the power law behavior that you get is going to depend on your initial conditions in a strong sense. Okay, so here's what you get. Here you can get a -3 power law. This is for decaying turbulence. You can get other types of power law behavior. You can also get the 5/3. It really depends on what sort of initial data you're putting in. And the idea here, when you're looking at decaying turbulence, or when people study decaying turbulence, is to try to put in some initial conditions so you'll get the minus 5/3 law for a long enough time. Okay, but it's never going to be a steady state because you don't have any driving. So you can get different results, and it's going to depend on your initial conditions. So if we really want to compare things correctly, we have to add, I'm really sorry, we have to add a driving force to both sides. And then the question is, how do we do that in terms of gravity? So we want this theory of gravity to have a driving force. And then if it has a driving force, we can reach a steady state, and then we can really compare it to something like this. So the way we're going to go about doing this is the following. Instead of adding a driving force to our hydrodynamic theory, we're going to place it on a background metric which is fluctuating. So the force or the randomness is going to be associated with a metric which is not Euclidean. So the metric is going to be fluctuating. Its average is just going to give us the Euclidean metric. This is a non-relativistic system I'm looking at. Okay, but you can pretend that, you know, whatever connection we're going to add to our covariant derivatives, you can treat that as some sort of driving force. Okay, so the randomness of the geometry that the fluid is in will give us the equivalent of a random force. And the reason we're doing this is that this is something that we can actually implement from the gravitational perspective. Alternately, we can just add a gravitational potential, which, oh, this should be 0. We should add a gravitational potential whose average is 0. So we have some gravitational force, which is 0 on average, but it's going to fluctuate, and that's going to be our driving force. So these things, the reason I'm going to look at that is that these are easier to implement in terms of the gravitational description. Okay, so the question is, what's going to happen here? Are we still going to see this 5/3 law? And also, how are we going to implement it? So implementing it is, at least in principle, simple. What we need to do is to solve this set of equations, but with boundary conditions at asymptotic infinity, where the boundary value of the metric isn't just going to be Minkowski space, but it's going to be some fluctuating metric. Okay, so this is how we want to solve this set of equations. And what we're going to get is a stochastic theory of gravity. So now, because our boundary conditions are random variables, it means that the metric is also, the entire space-time metric is going to be fluctuating. So it's going to be a random variable. And this is what we need to solve. So in practice, we have this Einstein equation. And for early times, we say we just have a black hole that's not doing anything. And at late times, we want the value of the metric at infinity to take on some value which is fluctuating around flat space. So Q here is a random variable, and this metric is going to be fluctuating. So we can use this metric, We can use one where the fluctuations are in the shear part of the stress tensor. We tried both options. So Q here is big Q is a random variable. It satisfies this differential equation. It's called an Ornstein-Uhlenbeck process. This one, where Xi is some sort of white noise. So Xi is something that we put in by hand. It's white noise. Its average is 0. Its two-point function is a delta function in time, and in space, it's peaked around some momentum. So in Fourier space, it's a delta function. In real space, it's going to be some sine function.
What's the meaning of the non-stochastic part that just comes from the Einstein equations? That Q dot equals minus Q over tau?
Well, yes. So the reason we didn't just say Q equals Xi, naively you'd say Q equals Xi and you're done. The problem is that if you plug this into the Einstein equation, you're going to get some powers of your random variable and derivatives of the random variable. And a time derivative of white noise is just not well defined. So this is an extra technical thing that we needed to add so that derivatives of our random variable will be well defined.
What is tau?
Okay. Pardon?
What is tau?
Tau is a parameter which says essentially what the correlation length of the random variable Q is. So Q, if you solve, you can actually solve this equation as a stochastic differential equation, and you'll find that Q is exponentially decaying with size with length tau. So what we're essentially saying is that instead of white noise, we're using an exponentially decaying correlator. So instead of a delta function, there's going to be some exponential decay, and tau is the width of this decay.
And dot is d to d tau.
Dot is dd tau. No, dot is ddt.
Okay. And tau
is a parameter.
Okay, good. Thank you.
Okay, good. Sorry. Okay, there's an extra technicality that I won't go into. And then we can just, And then we can just read the stress tensor from the metric. So remember, there's this relation between the actual solution for the metric and the stress tensor of the associated fluid. So once we solve this set of equations, we can read it. And after averaging, we'll get the average stress tensor, and that should give us some insight into the fluid behavior. Now, you can't solve this analytically, so we have to resort to numerics. And so we discretize our space-time. We have everything on a grid, and we put the x1 and x2 coordinates to be periodic. So we're really on a very large torus. And once you do this, there's an algorithm for solving these equations, and we just follow the algorithm. We solve this equation many, many times, and we computed averages. Here is what the energy momentum tensor looks like. So what you're seeing here is the energy momentum tensor. This axis here is x2. This axis here is x1. It's the spatial coordinates. What you're really seeing is the driving. So this scale here is 1 over the momentum scale associated with the driving force. The driving in this case is dominating the dynamics. So what we're seeing is the driving. When we do a Fourier decomposition, we can always just get rid of just ignore the part where the driving force is and see the rest of the physics. We'll see that in a minute.
Averaging, you average over what?
Over ensembles. So we do this. The driving force is taken from some ensemble. The white noise that's associated with the metric fluctuations is taken from an ensemble. So we just run this many times, and we can either time average or we can ensemble average, and you get pretty much the same results. So remember that there was the metric on the boundary went like minus 1 plus q dt squared. Oh, sorry, dt squared. And this q was, it was associated with some random variable, which you can roughly think of as psi. And so psi is, when you run the thing, you say, okay, give me at t equals 0, you pick up one value of psi, and then at t equals delta t, you pick another value of psi, and then you do this again and again and again and again, and you get some evolution. That evolution is not stochastic. That evolution is deterministic, right? I mean, if I give you the same values of psi that I pick, you'll be able to reproduce the solution. So there's nothing random about that. To really talk about randomness, we have to do that experiment many, many, many times and average. Either average over ensembles or average over time if the system is homogeneous. And then we get some sort of average quantity. So that's the average. The average is average over ensembles. Okay. So we did this. We extracted the velocity field. We have a relativistic velocity that we can read off the stress tensor, and from that we can read the non-relativistic velocity, and we get values which are sufficiently low. And then we can compute the energy power spectrum, and we find a very nice minus 5 Hertz behavior.
Just to understand, when you speak of the energy momentum tensor, you mean the pseudo tensor, like for gravitational perturbations?
No. Let me go back. I know I'm over time, so I'm trying to be quick about it. No. So what I mean here, so I still have just the Einstein equation. So I'm solving, this. Right? This is the set of equations I'm solving. There's no stress tensor here. But this set of equations is equivalent to this set of equations.
I see. So that's already a fluid stress tensor, basically.
Yes. The relation between them is that the metric itself is some known function of these parameters. So if I solve numerically this equation, I know what the metric is, and then I can just read off these parameters, or I can read off what the stress tensor is.
I see. Thanks.
Again, they're mapped to each other in an analytic way. So I say stress tensor, but it's the same object. It's just different. You just have to massage them to go from one to the other. Okay, so we can compute the energy power spectrum once we have the velocity, and we get this plot. Yeah, I can't erase this thing for some reason. But what you see here, this big peak here at 20 is where the driving force is. So here, this is roughly kf. And you see that it's so high, we had to cut it off. This is essentially these little squares that we saw in the plot. Everything is dominated by the driving force because it's very large. But below this driving force, you see the energy power spectrum as a function of time. So each line here corresponds to a different time at which we measured the energy power spectrum. So at t equals 0, we just had a state where we had a black hole, and then we started exciting it. So you see that the configuration converges to one where the energy power spectrum has a minus 5/3 power law. I'm sorry for this line that I can't erase. Okay, so this is one of our main results, but I think I'm over time. So let me just stop here. I think it's a good place to stop. So thank you.
Thank you.
Thanks, Amos, for a very interesting talk. We had a lot of questions, but any more questions?
So Amos, regarding your final result, you said it is minus 5.3, but what is how precise, or what is the error?
Yeah. So the error is very big here. So it's as plus minus 0.1, if I remember correctly.
Okay.
So I mean, and you can also see that the inertial range is just barely 1 decade, which is a little bit small.
Okay.
So we can't really say anything about anything precise yet. We really need some more serious numerics to get this right. Now, there's something else that I didn't mention because it would have just taken me too long. This is really a fluid because we wanted to we wanted to have the least amount of numerics, complications in numerics. We have this fluid that we're describing is really a fluid in 2+1 dimensions and not in 3+1 dimensions. So the fluid that you're seeing here, it really lives in x1, x2 space. So it's a 2+1 dimensional fluid. There you don't have a direct cascade. You have something called an inverse cascade. And then there's some physics that's very interesting. But at the end of the day, Kolmogorov's prediction for the inverse cascade is again minus 5/3. But what's surprising is that in 2+1 dimensions, Kolmogorov's prediction actually works for all powers of the momentum difference. So this plot I showed you, the difference between simulations and theory, in 2+1 dimensions, they coincide.
I see.
So again, the 5/3 we got, we don't know if it's 1.66 or 1.76. We can't really tell. That's the answer to your question, but to put it in a slightly broader perspective, there are lots of bits and pieces here that are also interesting in regards to this result.
I have a couple of questions regarding this last figure that we see here. When you explained, well, first of all, thank you for the talk and especially for explaining for us the background for Kolmogorov scaling. And now to the plot. In a previous plot, you described how the forcing is pumped at some K, and then it cascades into higher Ks, namely to smaller scales. And here we see the opposite, that you see this cascade at smaller K rather than a higher K. So that's that differs from the expectations, does it?
Yeah. So again, this has to do with the fact that you're right. This has to do with the fact that we're in 2+1 dimensions. So in 2+1, the dimensionality in the fluid really makes a difference. 2+1 is very different from 3+1. In 2+1, you get something called an inverse cascade. So the energy actually cascades in the opposite direction. So this is expected in 2+1 dimensions. That's the punch.
That cascade was in 3 dimensions. The direction
that
of
cascade was in 3 dimensions.
The background was in 3 dimensions, and the simulation was in 2.
So no, I mean no. Well, I was doing the simulation is in ADS4.
No, I understand, but the simulation is effectively
those
2+1 turbulence. While the earlier slide of the background was in 3+1 turbulence.
Yes. So you're absolutely right, but I just couldn't squeeze in all this in an hour, but you're right. Yes.
Okay. Another thing, I want to ask you whether I can slightly adjust the title that you were using. So this is, of course, a matter of taste, and hopefully it's okay to ask it. Could I say observation of turbulence observation of Kolmogorov scaling, in holographic turbulence? Would that be also a good title?
Yes. So, but since you asked, let me just tell you sort of what the goal here is. I mean, you could say, fine, you reproduce something that you expect to get, it might not be that interesting. But the eventual goal here, at least
I
my
wasn't
goal,
saying that.
Oh, no, not you, but one may say that. I'm not trying to insinuate that you're saying it. But I think, at least for me, what I would like to do is to be able to really get a handle over this power law behavior. What I mean is, right now, what we did was, so far in this talk, is to do some gravitational computation, transform it to some variables which look like hydrodynamics, and reproduce results in hydrodynamics. But the information about these power law behavior is hidden somewhere in the Einstein equations. And so there should be some geometric way to parameterize this power law behavior. And what I didn't, so my overall goal is to be able to somehow predict this power law behavior from properties of the Einstein equations and maybe black holes. One idea that's on the market is that once you add this stochastic driving force, the event horizon, if you look at it at scales of order of the inertial range, it'll have some sort of fractal behavior. And that fractal and the fractal dimension would be associated with this power law. So if you can somehow predict that, then you'd be able to make a prediction of this power law behavior from not by thinking of it in terms of hydrodynamic variables, but thinking of it in terms of gravity. And one thing that I didn't say, but one thing that we did do was, you remember we had this E of R where we averaged the shear tensor squared over a certain region. You can actually relate that to the extrinsic curvature of the horizon, the average value of the extrinsic curvature of the horizon squared. So there's this interplay between geometric quantities, the purely geometric quantities, and hydrodynamic quantities. And my goal is to be able to predict these things just from geometry. So this is where I'm going. And the first step is just to reproduce stuff that's well known.
Well, thank you. Yes, the way I see it is that once we know that that this gravitational setup is equivalent to turbulence, we can expect and predict, to hydrodynamics. This gravitational setup is equivalent to hydrodynamics. We can expect and predict turbulence and Kolmogorov scaling. But it is very interesting to observe it. It's one thing to predict, and it's another thing to observe. Secondly, you had to overcome the implementation of the forcing, and you implemented it in a way which is not fully clear that it is the same forcing in the hydrodynamic problem, and the proof of it is in the result.
Yes. No, I agree. I agree. This is an interesting result. But I'm looking further ahead to things that I think are stronger. Thank you.
Thanks.
Any more questions? Maybe I'll ask a quick one, since we're over time. But so regarding the direct cascade, so do you? I mean, so if you do the same in ADS5, for example, do you expect to see a direct cascade? Has this been done?
It hasn't been done. So the problem is that if we're working in ADS5, you have 5 coordinates. Each time you add another direction, the number of grid points grows, like a power. So instead of having 200 cubed points, you'll have 200 to the 4th grid points. So and even so, just even now when we have only ADS4, our result isn't as precise as we'd like it to be. Mm-hmm. Going to ADS5 is just, I think, is hard. So it hasn't been done. And again, this is you need people who are more serious in numerics than we are to do this. It would be very interesting, but it's very hard.
Yes. Or you could use a smaller grid.
Yes.
A smaller spacing.
Amos.
Yeah.
You showed two types of black hole, and you mentioned you will look on only one of them, right?
Yes. Yes.
Because turbulence, what was the problem with the other one? Turbulence does not appear or something like that?
No. So, well, it's
not
not
two kinds of black holes. It's a black plane and a black hole, and he wants a black plane.
Okay.
Yeah.
The black
There was a
brain and
problem
a
with the
black
words
hole.
used.
Yeah, so Barak is right. I'm saying black hole, even though these are really, even though it's a black brain and a black hole, this is language that, you know, people just say black hole, even though they shouldn't. So the reason I'm looking at this is really because of this nice relation here. This relation between a fluid description and gravity is best captured by the black brane. Now, if you take a black hole, spherical one, what you can do, well, what you can argue is that it's going to be related to some fluid on a sphere. But when you describe fluid on a sphere and you want to take into account that the sphere is actually curved, that already generates lots of complications. So often when people think about fluid on a sphere, they assume that I just have Navier-Stokes equations on a sphere and that's it. But you can have extra curvature terms that do things for you on the sphere. And those will appear in some naturally in some sense. So unless you say that the curvature is small, you're going to get some hydrodynamics on a sphere, and it might be interesting to look at, but the relation is going to be complicated. And if you say that the curvature is sufficiently small that you can ignore the sphere, then you're back to the black brane.
Okay.
So that's why it's less studied. But in principle, if you do this, what you're going to get is turbulence on a sphere.
It will be a generalization in some way?
I don't think it's a generalization. Well, it depends. I don't know. The fluid description is much harder. And again, you're going to get fluids on the surface of a 3-sphere or a 2-sphere if you want. Physics is different. I mean, there's interesting things. You can have it rotate and, you know, you could ask about it. But even the fluid description is a little bit tricky. So I think it can be done, but you have to work it out carefully.
Okay, thanks.
Okay, great. So if there are no further questions, let's thank Amos again.
Okay, thank you.
Thank you. I'll close the recording.